Imagine standing somewhere on Earth where you are more alone than almost anywhere else possible. Not alone in a desert where someone might pass through. Not alone on a mountain where a village sits somewhere below. But alone in a way that feels complete. The closest person to you is not on land. They are not on another boat. They are orbiting above you in space, floating hundreds of kilometers overhead in a station that circles the planet. This place exists. It sits in the middle of the Pacific Ocean, so far from everything that reaching it takes days of travel across open water. No islands appear on the horizon. No ships cross your path. No birds circle overhead looking for food. The water stretches in every direction without change. Blue meets blue at a line, so distant it barely seems real. This is Point Nemo, the oceanic pole of inaccessibility, the most isolated location on the surface of Earth. It earned this title not through mystery or legend, but through simple mathematics. Scientists measured the distance from every shoreline on the planet. They found the exact spot where all those distances reach their maximum. That spot sits more than 2,600 kilometers from the nearest land in any direction. To put that in perspective, it is roughly the distance between London and Cairo. Except instead of countries and cities between them, there is only ocean. Deep, calm, and endlessly repeating. Most people will never see this place. Most will never need to. It offers nothing that draws visitors. No resources to harvest. No beauty that photographs can capture better than any other stretch of sea. No reason to go there except to say you did. Yet this emptiness has made it useful in an unexpected way. When satellites and space stations reach the end of their lives, they must come down. Space agencies cannot let them fall randomly. Debris could strike cities, ships, or fragile ecosystems. So they aim for the safest place they can find. A place where almost nothing lives. Where almost no one travels. Where the ocean can absorb the impact without consequence. Point Nemo became that place. Over the decades, hundreds of objects launched into orbit have returned here. Modules from research stations. Fuel tanks from rockets. Satellites that once transmitted signals across continents. All of them guided down through the atmosphere until only the heaviest pieces survived. Those pieces splashed into these remote waters and sank. They rest now on the seafloor, thousands of meters below the surface, scattered across an area larger than many countries. Silent, invisible, slowly corroding in the cold and dark. This makes Point Nemo one of the strangest places on Earth. A region almost entirely empty of natural life, yet filled, in a way, with the remnants of human achievement. The ocean here holds more traces of space exploration than almost anywhere else. Not because people wanted it that way, but because isolation made it the only logical choice. Tonight, we will drift across this vast stretch of water. We will explore why it remains so empty, why the currents move as they do, why sailors once feared crossing areas like this, and why the deep-sea floor beneath it has become an unintended museum. A place where machines built to explore the stars finally come to rest. The story of Point Nemo is not loud or dramatic. It unfolds slowly, like the currents that circle it. It asks for patience, the same patience required to cross an ocean where nothing breaks the view. So settle in. Let your thoughts drift as we begin this journey. There is no rush to reach the end. The destination is understanding, not arrival. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries, consider subscribing. We create these videos to help you relax and learn at the same time. Let the information wash over you gently as we explore together. Every location on Earth exists in relation to something else. Cities connect to roads. Mountains rise near valleys. Islands float within sight of other islands. But one point on the planet has no such relationship. It exists in perfect isolation. When cartographers set out to find the most remote location on Earth, they did not search for drama. They were not looking for beauty, danger, or symbolic meaning. They wanted a simple answer to a mathematical question. Where is the point farthest from all land? The calculation required measuring distances from thousands of coastlines. Every continent, every island, every reef had to be considered. The process involved algorithms that tested millions of potential coordinates. Each time, the distance to the nearest land was measured in all directions. The goal was to find the spot where that minimum distance reached its maximum value. After running the calculations, the answer emerged. A point in the South Pacific Ocean, located at approximately 48 degrees south latitude and 123 degrees west longitude. This spot sits more than 2,600 kilometers from the nearest shoreline. The closest land masses form a triangle around it. To the north lies Juicy Island, part of the Pitcairn Islands. A tiny, uninhabited piece of coral barely rising above the waves. To the northeast sits Moto Nui, near Easter Island, a rocky outcrop known more for history than for size. To the south lies Maher Island, off the coast of Antarctica, a frozen, lifeless point covered in ice and snow. None of these places are easy to reach. None support large populations or regular visitors. And Point Nemo sits so far from all three that even them seem impossibly distant. The name itself comes from Jules Verne's famous character, Captain Nemo, a man who chose the sea as his refuge from the world. The word Nemo also means no one in Latin. It is a fitting label for a place where no one goes, where no one lives, and where even the idea of presence feels strange. Standing at Point Nemo, if such a thing were possible, would create an unusual sensation. You would know that traveling in any direction for days would bring you no closer to land. The horizon would remain unchanged, no matter which way you looked. The sky would stretch overhead without interruption, and the water would continue rolling in the same gentle patterns. The isolation is not just physical. It is psychological. Humans orient themselves using landmarks, references, and boundaries. We need these things to feel located. Point Nemo offers none of them. It is a coordinate on a map, nothing more. But the meaning of that coordinate is profound. It tells us that Earth, despite being completely explored and mapped, still contains places beyond human presence. Places where our absence defines the environment more than anything else. The space station that orbits overhead comes closer than any person on land. At its nearest point, astronauts aboard the International Space Station float roughly 400 kilometers above the ocean. Meanwhile, the closest dry ground sits more than 6 times that distance away. This comparison captures the strangeness perfectly. You would be closer to people in space than to people on Earth. The realization reshapes how we think about proximity and isolation. It reminds us that distance is not always measured in straight lines. Sometimes it is measured in barriers. And the ocean, vast as it is, becomes the ultimate barrier here. Nothing about Point Nemo looks unusual from above. Satellite images show only blue water. The surface reflects sunlight the same way it does everywhere else. Waves form and dissolve in predictable rhythms. Clouds drift overhead, shaped by wind and temperature. There is no visual marker, no physical feature that signals you have arrived. The only way to know you are there is through instruments. A GPS reading, a calculated position, numbers on a screen confirming that you have reached the point farthest from everything. This invisibility is part of what makes the location fascinating. Most extreme places on Earth announce themselves. The highest mountain is obvious. The deepest trench can be mapped. The coldest place shows its nature through ice and wind. But Point Nemo remains silent. It does not announce itself. It simply exists, quietly, in the middle of the largest ocean on the planet. The mathematics that define it are elegant in their simplicity. They require no interpretation, no debate. The numbers are exact. And yet, despite this precision, the place feels abstract. It is real, but intangible. Measurable, but impossible to hold. A point on a sphere that represents the furthest edge of human absence. Understanding this isolation is the first step. Because everything else about Point Nemo flows from this one fact. The emptiness, the currents, the lack of life, the use as a spacecraft cemetery. All of it begins with distance. With the simple reality that nothing else is nearby. And that distance, more than anything else, shapes the story of what lies here. Now that we understand how far Point Nemo sits from everything, we can begin to ask the next question. What does that distance create? What happens to an ocean when it remains untouched by land for so long? The Pacific Ocean is the largest body of water on Earth. It covers more surface area than all the continents combined. Within it lie thousands of islands, countless ecosystems, and currents that shape global weather. But even in something so vast, there are places that stand apart. Places where the ocean becomes something different. Not because of what it contains, but because of what it lacks. Point Nemo sits in one of these places. A region so far from the influences of land that the water takes on a different character. It becomes clear, still, and almost entirely lifeless. Not because anything prevents life from existing, but because the conditions necessary for life to thrive simply are not present. No rivers carry nutrients from mountains. No coastlines create sheltered bays where organisms gather. No upwelling currents bring food from the deep. The water here is isolated in the same way the location is isolated. It moves in slow circles, keeping itself separate from the rest of the ocean. And within those circles, the sea becomes one of the quietest places on the planet, both above the surface and far below it. Understanding this emptiness requires looking at the ocean not as a single body of water, but as a system of layers, currents, and chemical balances, each one playing a role in shaping what can survive here, and each one showing us why Point Nemo remains so barren despite being surrounded by water. Let us continue. When people think of deserts, they imagine sand, heat, and dryness. But the ocean has deserts too. Places where life cannot flourish despite being surrounded by water. Point Nemo sits in the largest of these oceanic deserts. Life in the ocean begins with sunlight and nutrients. Tiny organisms called phytoplankton float near the surface. They absorb light and use it to convert carbon dioxide and water into energy. This process, photosynthesis, forms the foundation of the entire marine food web. Without phytoplankton, there are no zooplankton. Without zooplankton, there are no small fish. Without small fish, there are no larger predators. Everything depends on these microscopic organisms thriving near the surface. But phytoplankton need more than sunlight. They need nutrients. Nitrogen, phosphorus, and iron must be present in the water for them to grow. These nutrients typically enter the ocean through rivers, rainfall, or upwelling currents. Rivers carry minerals from land into coastal waters. Rainfall delivers small amounts of nutrients from the atmosphere. Upwelling currents bring deep, nutrient-rich water to the surface. At Point Nemo, none of these sources exist in meaningful amounts. The nearest land is too far away for rivers to deliver nutrients. Rainfall is sparse and irregular, and the currents here do not create upwelling. Instead, they trap surface water in a stable, circular pattern. This pattern is called a gyre. The South Pacific Gyre is one of the largest on Earth. It rotates slowly, driven by wind and the planet's rotation. Water caught in this gyre can remain there for years, even decades. During that time, organisms consume whatever nutrients exist. But nothing replenishes them. The gyre isolates the water, keeping it separate from nutrient sources outside the system. Over time, the surface water becomes depleted. Phytoplankton populations drop to minimal levels. The water becomes clear because there are so few organisms to cloud it. Scientists call this oligotrophic water, water that is extremely low in nutrients. In productive ocean regions, the water often appears greenish or murky. That color comes from billions of phytoplankton absorbing sunlight. At Point Nemo, the water is strikingly blue, almost transparent. The clarity allows sunlight to penetrate unusually deep, sometimes more than 100 meters. But this transparency is not a sign of health. It is a sign of absence. Without phytoplankton, the base of the food web collapses. Zooplankton, which feed on phytoplankton, cannot sustain large populations. Small fish which feed on zooplankton pass through but do not linger. Larger predators avoid the area because there is nothing to hunt. Even seabirds, which typically follow schools of fish, rarely appear here. The result is an ocean that looks calm and pristine, but supports almost no visible life. The water is not toxic. It is not polluted. It simply lacks the chemical ingredients necessary for ecosystems to flourish. Scientists compare this region to a land desert for good reason. Both environments are defined by scarcity. In a land desert, the lack of water prevents most plants from growing. In an oceanic desert, the lack of nutrients prevents most organisms from surviving. The comparison is not perfect, but it captures the essence of the place. A vast expanse that appears rich, but offers little. The seafloor beneath Point Nemo is equally barren. In productive ocean regions, organic material sinks from the surface to the deep. Dead phytoplankton, fecal matter from zooplankton, and other particles drift downward. This material, called marine snow, feeds deep-sea organisms. At Point Nemo, very little marine snow falls. The sparse life at the surface produces minimal waste. The deep-sea creatures that depend on this food source must survive on an exceptionally limited supply. As a result, the deep sea here is just as empty as the surface. The temperature structure of the water also plays a role. The surface layer is warmed by constant sunlight. Warm water is lighter than cold water, so it stays on top. Beneath it lies a layer of much colder water, rich in nutrients. The boundary between these layers is called the thermocline. At Point Nemo, the thermocline is strong and stable. It acts like a barrier, preventing the cold, nutrient-rich water below from mixing with the warm, sunlit water above. Without mixing, the nutrients remain locked in the deep. The phytoplankton at the surface cannot access them. This stratification reinforces the emptiness. Even seasonal changes do not break the pattern. In some parts of the ocean, winter storms churn the water and bring nutrients to the surface. But the South Pacific gyre is remarkably stable. Storms weaken before reaching this region. Winds are generally calm. The water remains layered and undisturbed. The lack of life has consequences beyond biology. It affects the ocean's ability to absorb carbon dioxide. Phytoplankton play a key role in removing carbon from the atmosphere. When they photosynthesize, they take in carbon dioxide. When they die, some of that carbon sinks to the deep ocean. This process, called the biological carbon pump, helps regulate Earth's climate. But at Point Nemo, the biological carbon pump operates at minimal capacity. With so few phytoplankton, less carbon is absorbed. The ocean here contributes little to global carbon cycling. It is a region that sits quietly, almost passively, within the larger climate system. Despite the emptiness, the water is not completely sterile. Microorganisms exist in small numbers. A few species of bacteria and archaea drift through, adapted to extreme scarcity. Some deep-sea fish pass through the region on long migrations. Occasionally, a whale or dolphin crosses the area, traveling between more productive waters. But these appearances are rare and brief. Nothing stays at Point Nemo for long. The environment offers no reason to linger. Understanding this emptiness is essential, because it explains why the region became useful for something entirely unrelated to nature. When humans needed a place to safely dispose of spacecraft debris, they looked for an area with minimal life. A place where falling objects would not harm ecosystems or people. Point Nemo, with its vast emptiness and isolation, became the obvious choice. The ocean's natural barrenness made it the perfect destination for machines returning from space. The emptiness of Point Nemo is not an accident. It is the result of currents, distance, and chemistry working together over vast timescales. But this same emptiness created an opportunity, a way for space agencies to solve a problem that had no other solution. Every object launched into space must eventually come down. Satellites stop functioning. Space stations reach the end of their operational lives. Rocket stages complete their missions and begin to decay in orbit. Some of these objects burn up completely when they re-enter the atmosphere. The heat and friction are so intense that nothing survives. But not everything disintegrates. Large structures, especially those made of dense metals, can survive the descent. Fuel tanks, engines, heavy structural components. These pieces fall through the atmosphere, still burning, still fragmenting. But they do not vanish. Eventually, they reach the ground, or in most cases, the ocean. Space agencies face a critical question: when planning these re-entries. Where should the debris land? Letting it fall randomly is not an option. A piece of metal weighing hundreds of kilograms, traveling at high speed, could cause catastrophic damage. It could strike a city, a ship, or a populated area. It could harm ecosystems or contaminate water sources. So agencies carefully calculate where the debris will land. They need a location that is large, remote, and empty. A place where the risk of harming anyone or anything is as close to zero as possible. For decades, Point Nemo has served this purpose. The same isolation that makes it unreachable also makes it safe. And so, one by one, machines that once orbited Earth have been guided here, sent on a final journey through fire and air, ending their existence in the deep waters of the most remote ocean on the planet. Beneath the waves at Point Nemo lies a collection unlike any other on Earth. Not a natural formation, not a shipwreck, but the remnants of humanity's reach into space, scattered across the seafloor in silence. Since the 1970s, space agencies around the world have used this region as a controlled re-entry zone. When a spacecraft or satellite can no longer function, it must be removed from orbit. Leaving it in space creates hazards for other missions. Dead satellites can collide with active ones. Debris can damage functioning equipment. The solution is to bring the object down safely. For smaller satellites, this often means letting them burn up completely in the atmosphere. But for larger structures, complete disintegration is not guaranteed. The most famous example is Mir, the Russian space station. Mir operated in orbit for 15 years, from 1986 to 2001. It was a massive structure, one of the largest objects ever placed in space. When its mission ended, Russian engineers faced the challenge of bringing it down safely. They calculated a trajectory that would guide the station into the atmosphere at a precise angle. Most of Mir burned up during re-entry. The heat was intense enough to destroy much of the structure. But some pieces survived. Heavy components, dense materials, sections that could withstand the extreme temperatures. These fragments fell into the ocean at Point Nemo. The event was carefully monitored. Engineers tracked every stage of the descent. They confirmed that the debris landed within the target zone. No ships were nearby. No land was threatened. The ocean absorbed the impact, and the pieces sank into the deep. Mir was not the first object to end its journey here. And it was not the last. Dozens of spacecraft, rocket stages, and satellite components have been directed to this region. Some were Soviet-era missions. Others came from European, Japanese, and American space programs. The objects vary in size and purpose. Some were research satellites designed to study Earth's atmosphere. Others were cargo vehicles that ferried supplies to space stations. A few were experimental platforms testing new technologies. All of them eventually reached the end of their usefulness. And all of them came down here. The process of controlled re-entry requires precision. Engineers must calculate the exact moment to fire retro-rockets or adjust the orbit. They account for atmospheric drag, the object's mass, and its altitude. The goal is to ensure that the debris lands within a designated area. Point Nemo provides a large target. The region around it spans hundreds of kilometers. Even if calculations are slightly off, the debris will still land far from any populated area. This margin of safety makes the location invaluable. When a spacecraft re-enters, It does not fall gently. The descent is violent. The object accelerates as it drops toward Earth. Air resistance creates friction, generating temperatures hot enough to melt steel. Panels peel away. Insulation burns off. Bolts and joints fail under the stress. By the time the object reaches the lower atmosphere, it is fragmenting rapidly. Most of what remains is unrecognizable. Twisted metal, scorched surfaces, broken components. When these fragments hit the water, they create splashes that go unwitnessed. No ships are present to see the impact. No cameras capture the moment. The debris strikes the surface and immediately begins to sink. The ocean here is thousands of meters deep. The pressure increases rapidly as the fragments descend. Any hollow structures collapse. Air pockets are crushed. The pieces continue falling through the darkness until they reach the seafloor. Once they settle, they become part of the landscape. The seafloor at Point Nemo is covered in fine sediment. The fragments rest on this sediment, separated by large distances. Some pieces are small, no larger than a piece of furniture. Others are massive, weighing tons. Over time, the ocean begins to reclaim them. Salt water is corrosive, especially to metals. Even in the cold, oxygen-poor conditions of the deep sea, corrosion occurs. Surfaces slowly degrade. Edges become rounded. Details fade. But the process is slow. Some fragments may remain recognizable for decades, even centuries. The collection continues to grow. As more missions reach the end of their lives, more debris is directed here. Space agencies coordinate these efforts to avoid conflicts. They share information about planned re-entries. They ensure that multiple objects do not arrive at the same time. The goal is to manage the process responsibly, to minimize risk, and to use the isolation of Point Nemo as a tool for safety. Some people refer to this region as a spacecraft graveyard. The term is evocative, almost poetic, but it is also slightly misleading. A graveyard implies a place where things are laid to rest deliberately, with care and ceremony. The seafloor at Point Nemo is not like that. It is simply the place where things land when they fall. There is no monument, no marker, no acknowledgement of what lies below. The ocean hides everything. The debris is invisible from the surface. Even with advanced sonar, mapping the individual fragments would be extremely difficult. They are scattered over such a large area that locating them would require immense effort. And there is no practical reason to do so. The fragments pose no threat where they are. They do not leak harmful chemicals. They do not disturb the sparse ecosystems of the deep. They simply exist, silent and forgotten. Yet there is something haunting about the idea. These objects once represented the pinnacle of human engineering. They were built with precision, launched with careful planning, and operated for years in the harshness of space. They transmitted data, supported astronauts, and expanded our understanding of the universe. Now they rest on the ocean floor, their purpose fulfilled, their stories ended. It is a reminder of impermanence. Even the most sophisticated machines eventually wear out. Even the grandest projects have final chapters. And when those chapters close, the machines return to Earth. Not to museums or archives, but to the deep, where the planet quietly absorbs them once more. The spacecraft that rest beneath Point Nemo did not arrive by chance. They followed paths shaped by forces beyond human control. The same currents that keep the surface waters empty also influence how debris moves once it lands. Understanding these currents helps us see why this region remains so isolated. Water never stays still. Even in the calmest seas, currents move beneath the surface. They flow in patterns shaped by wind, temperature, and the rotation of the Earth. These patterns connect oceans across the globe. They distribute heat from the equator to the poles. They carry nutrients from deep waters to shallower zones. They shape the movement of everything that floats or drifts. At Point Nemo, the currents follow a specific pattern, one that has remained stable for thousands of years. The water here moves in a vast circle, looping through the South Pacific. This circular flow is called a gyre, and it plays a central role in maintaining the isolation of this region. The gyre acts like a boundary. Water inside it stays inside. Water outside rarely enters. The result is a system that keeps itself separate from the rest of the ocean. Understanding how this system works requires looking at the forces that drive it. The wind that blows steadily across the surface. The temperature differences between warm and cold water. And the subtle but powerful effect of the Earth's rotation. Together, these forces create a current that shapes everything about Point Nemo. From the clarity of the water to the lack of life. From the stability of the environment to the way debris settles after falling from space. Let us follow the current and see where it leads. Imagine a river with no banks. A current that flows in a loop, never reaching a destination. This is what shapes the waters around Point Nemo. A slow, steady circle that has turned for millennia. The South Pacific Gyre is one of 5 major gyres in the world's oceans. Each gyre is a massive system of rotating currents. They are driven primarily by wind patterns. Trade winds near the equator blow from east to west. Westerly winds at higher latitudes blow from west to east. These opposing wind directions create a circular motion in the water. In the southern hemisphere, gyres rotate clockwise. The South Pacific Gyre is enormous. It spans thousands of kilometers. At its center lies Point Nemo. The currents here do not rush or churn. They move gently, almost imperceptibly. A floating object caught in the gyre might travel only a few kilometers per day. But over months and years, that movement adds up. The object would trace a wide arc through the ocean, never escaping the system, never finding its way to shore. The gyre's stability comes from its size and the consistency of the winds that drive it. Unlike coastal currents, which are disrupted by land, the South Pacific Gyre flows uninterrupted. There are no continents to block its path, no islands to redirect its motion. The water simply moves in a continuous loop. This stability has important consequences. It prevents mixing between the surface and the deep. In many parts of the ocean, storms and strong winds churn the water. They break the boundary between warm surface layers and cold, deep layers. Nutrients from below rise to the surface. But at Point Nemo, the winds are generally calm. Storms are rare and weak. The water remains stratified. The thermocline stays intact. Nutrients remain locked in the deep, inaccessible to the organisms that need them. The gyre also isolates the water chemically. Water trapped inside the system can remain there for years. During that time, organisms consume whatever nutrients exist. But because the gyre is so far from land, no new nutrients arrive. Rivers do not reach this far. Atmospheric deposition is minimal. Upwelling does not occur. The water becomes increasingly depleted. Over time, it transforms into some of the clearest, most nutrient-poor water on Earth. The clarity is striking when viewed from above. Satellite images show the South Pacific Gyre as a deep, vivid blue. The color indicates low concentrations of chlorophyll, the pigment found in phytoplankton. In productive ocean regions, chlorophyll levels are high. The water appears greenish or murky. At Point Nemo, chlorophyll levels are among the lowest measured anywhere. The water is so transparent that it absorbs very little light. This gives it an almost unnatural appearance. A blue so pure it seems artificial. The gyre also affects how objects move through the region. Anything that enters the system, whether natural or human-made, becomes subject to its flow. Drifting debris circulates slowly. Organic material breaks down over time, but the pieces remain within the gyre. Even spacecraft debris, after landing on the seafloor, is influenced by deep currents that form part of the larger system. These deep currents move even more slowly than the surface currents. Water at the bottom of the ocean can take centuries to complete a circuit. But it still moves, following patterns shaped by temperature and salinity. The gyre connects surface and deep in a slow, continuous exchange. Though the exchange happens so gradually that it barely affects conditions in any noticeable way. Another consequence of the gyre is its role in isolating marine species. Many ocean organisms rely on currents to disperse their larvae. Eggs and young drift with the water, spreading across wide areas. But in the South Pacific Gyre, larvae that drift too far from productive regions may not survive. The lack of food prevents them from developing. They starve before reaching maturity. This limits the number of species that can inhabit the region. Only the most adaptable, the most efficient, can persist here. The gyre also influences global ocean circulation. It is part of a larger system that moves water around the planet. Water from the South Pacific Gyre eventually connects with currents flowing toward the poles. It carries heat, dissolved gases, and trace elements. These contributions are small compared to more active regions, but they are part of the intricate web that regulates Earth's climate. Changes in the gyre can have far-reaching effects. If wind patterns shift due to climate change, the gyre's size and strength may change. If it weakens, mixing could increase, bringing nutrients to the surface. If it strengthens, stratification could become even more pronounced, further reducing productivity. Scientists monitor these changes carefully. The South Pacific Gyre serves as an indicator of larger trends. Its behavior reflects the health of the ocean system as a whole. For now, the gyre remains stable. It continues its slow rotation. The water circulates as it has for millennia. Point Nemo remains locked within this system. Isolated by distance, isolated by chemistry, and isolated by the steady, relentless current that circles but never stops. The gyre shapes the present, but it also connects to the past. Long before scientists mapped these currents, sailors crossed these waters. They left behind stories that echo the isolation we now understand scientifically. For centuries, sailors were the only humans who ventured into the vast stretches of the Pacific. They traveled without GPS, without detailed maps, without certainty. Navigation depended on stars, instinct, and experience. In some regions, they found landmarks to guide them. Islands, reefs, changes in the color of the water. But in other regions, there was nothing. Just water and sky, repeating endlessly. These empty stretches tested their resolve. Not because the ocean was dangerous there, but because the monotony wore on the mind. Days blended into weeks. The horizon never changed. The sea offered no feedback, no confirmation that they were making progress. Sailors wrote about this in their journals. They described the silence, the stillness, the feeling of being suspended in place. Some found it peaceful. Others found it unsettling. Point Nemo sits in one of these empty stretches, a place where sailors, even today, rarely go. But the few who have crossed nearby left impressions worth considering, because their words remind us that isolation affects more than just ecosystems. It affects people too. Let us listen to what they said. The wind blew steadily, but it carried no message. The waves rose and fell in patterns so regular they became background noise. One sailor wrote that after 3 weeks at sea, he stopped noticing the sound of water against the hull. It became like breathing, he noted, present but invisible to the mind. They wrote about time, how it seemed to slow when there were no events to mark its passage. Morning looked like afternoon. Afternoon looked like evening. The sun moved across the sky, but everything else stayed the same. Without landmarks to pass, without tasks that varied day to day, time lost its usual rhythm. Some sailors found this disorienting. They wrote about losing track of dates, forgetting which day of the week it was. Others found it meditative. One journal entry from the 1800s describes the experience as peaceful, like being held in the palm of something larger than understanding. Navigation became both easier and harder in these waters. Easier because there were no obstacles to avoid. No rocks, no shallows, no sudden changes in depth. The ocean floor lay thousands of meters below, far beyond concern. But harder because there were no references to confirm position. Celestial navigation worked, but it required clear skies. On cloudy days or nights, sailors simply maintained their heading and hoped. Dead reckoning, the practice of calculating position based on speed and direction, became essential. But even small errors accumulated over days. A vessel could drift dozens of kilometers off course without realizing it. Some sailors described a sensation they called the forgetting. After enough time at sea, the memory of land began to feel distant. Not forgotten entirely, but somehow less real. Ports, cities, even family members became abstract concepts. The ocean, meanwhile, became the only reality. The only thing that existed in the moment. One sailor wrote, "I could picture my home, but I could not feel it. The sea was all that mattered." This psychological shift was not unique to the South Pacific. It happened on all long voyages. But in regions like Point Nemo, where nothing interrupted the emptiness, the shift happened faster. The mind adapted to the environment by letting go of what was absent. Modern sailors report similar experiences. Even with advanced communication systems, GPS, and weather forecasts, the feeling of isolation remains. A cargo ship captain who crossed near Point Nemo in the 2010s wrote about it online. "You know exactly where you are, but it doesn't matter. There's nothing around you, no other ships on the radar, no lights at night, just you and the ocean." He described how the crew became quieter as they crossed the region. Conversations grew shorter. People spent more time alone, looking at the water. It's not uncomfortable, he wrote. It's just different, like the ocean is reminding you how small you are. Another recurring theme in sailor accounts is the clarity of the stars. Far from any light pollution, far from atmospheric disturbances caused by land, the night sky becomes extraordinarily vivid. Sailors described seeing stars they had never noticed before. Constellations appeared sharper, more detailed. The Milky Way stretched across the sky like a river of light. One journal entry from a 19th century voyage describes the stars as so bright they cast shadows on the deck. This clarity had practical value. Celestial navigation became more accurate, but it also had an emotional impact. Many sailors wrote about feeling connected to something vast and ancient. The stars had guided travelers for millennia. Looking up at them, in the middle of the Pacific, created a sense of continuity. A reminder that others had drifted through these same waters, under the same sky. Not all accounts were positive. Some sailors found the emptiness oppressive. One captain wrote about a crew member who became deeply anxious after 2 weeks without seeing land. The man could not sleep. He paced the deck at night, staring at the horizon as if willing something to appear. Eventually, he recovered after the ship reached port. But the experience left a mark. Another journal describes a navigator who became convinced they were traveling in circles. Despite their instruments showing steady progress, he felt as though the ship was not moving. The ocean looks the same every direction, he wrote. How can we know we are going anywhere? These reactions were rare, but they highlight the psychological toll of extreme isolation. Humans are not built for environments without variation. Our brains rely on change to maintain a sense of time, place, and purpose. When change disappears, the mind struggles to adapt. For most sailors, though, crossing regions like Point Nemo was simply part of the job. They did not romanticize it or fear it. They accepted it as a phase of the journey. Something to endure, something to complete. Their journals reflect this pragmatism. Entries become shorter, more factual. Wind direction, estimated position, condition of the sails. The emptiness did not inspire poetry. It inspired patience. What these accounts show us is that isolation affects people in different ways. Some find peace in it. Others find unease. Most find a mixture of both. But all of them agree on one thing. The Central Pacific is unlike anywhere else they traveled. Not because it was dangerous, but because it was so profoundly empty. And that emptiness stayed with them long after they left. Sailors described what they felt, but they could not explain what caused it. They did not know about gyres, stratification, or nutrient depletion. They only knew that the water seemed lifeless. Today, science gives us the answers they lacked. And those answers reveal why the emptiness is not just a feeling, but a measurable reality. Every environment on Earth operates according to rules. Deserts are dry because rain cannot reach them. Forests are lush because water and sunlight combine with rich soil. Coral reefs thrive because warm, shallow water supports symbiotic relationships. These rules are not flexible. They shape what can exist and what cannot. The ocean around Point Nemo follows rules too. Rules about nutrients, light, temperature, and mixing. When those rules create conditions that prevent life from flourishing, the result is an oceanic desert. Not a desert of sand, but a desert of scarcity. Science has spent decades studying this phenomenon, measuring the chemistry of the water, tracking the movement of currents, observing the sparse populations of organisms that manage to survive here. What they have found confirms what sailors suspected centuries ago. This region is fundamentally different from the rest of the ocean. Not in obvious ways, but in the quiet, invisible processes that determine whether life can thrive. Understanding these processes helps us see Point Nemo not as a mystery, but as a natural consequence. A place where the ocean shows us what happens when nutrients vanish and currents isolate. Let us look at the science behind the emptiness. Science does not deal in poetry. It deals in measurements, patterns, and cause. When scientists turned their instruments toward Point Nemo, they found something remarkable. Not because the region was full of life, but because it was so empty. The study of oceanic productivity begins with a simple question. How much life does the water support? To answer this, scientists measure chlorophyll concentrations. Chlorophyll is the pigment that allows phytoplankton to photosynthesize. Where chlorophyll levels are high, phytoplankton are abundant. Where levels are low, phytoplankton are scarce. Satellites equipped with special sensors can measure chlorophyll from space. They analyze the color of the ocean surface. Green tones indicate high productivity. Blue tones indicate low productivity. The South Pacific Gyre appears as a vast patch of deep blue. The measurements confirm what the color suggests. Chlorophyll concentrations here are among the lowest in the world. In productive regions, concentrations might reach several milligrams per cubic meter. At Point Nemo, they often drop below zero point 0.1 milligrams per cubic meter. That is a difference of more than 10 times. The scarcity of phytoplankton cascades through the entire ecosystem. Zooplankton, which feed on phytoplankton, are equally sparse. Studies using fine nets to collect zooplankton from the water show very low densities. In coastal waters, a single net tow might collect thousands of organisms. At Point Nemo, the same net might collect dozens. Fish populations are similarly affected. Commercial fishing vessels avoid this region because catches are too small to justify the trip. Even research vessels find it difficult to collect specimens. The fish that do live here are typically small, slow-growing species adapted to low food availability. Marine mammals are rare. Whales occasionally pass through while migrating between feeding grounds. But they do not linger. There is nothing here to sustain them. Seabirds, which often follow fishing boats or congregate near productive waters, are almost never seen. The few birds that cross this region are usually lost or blown off course. The lack of life is not just a surface phenomenon. It extends deep into the water column. Scientists have lowered instruments thousands of meters down. They measure temperature, salinity, oxygen, and nutrient levels at various depths. What they find is a stable, stratified system. The surface layer is warm and nutrient-poor. The deep layer is cold and nutrient-rich. The boundary between them is sharp and persistent. This boundary, the thermocline, prevents mixing. In other parts of the ocean, seasonal changes or strong storms can break down the thermocline. Wind and waves churn the water. Cold, nutrient-rich water rises to the surface. This process, called upwelling, fuels biological productivity. But at Point Nemo, upwelling does not occur. The winds are too weak. The water is too stable. The thermocline remains intact year-round. Without upwelling, the surface layer becomes a closed system. Organisms consume the available nutrients, and nothing replenishes them. Over time, the water becomes oligotrophic, extremely low in the nitrogen, phosphorus, and iron that life requires. Iron is particularly important. In many parts of the ocean, iron is the limiting nutrient. Even if nitrogen and phosphorus are present, phytoplankton cannot grow without iron. Iron typically enters the ocean through two pathways. Dust blown from deserts carries iron particles into the water, and hydrothermal vents on the seafloor release iron-rich fluids. At Point Nemo, neither pathway is active. The region is too far from any major desert. Dust from Australia or South America settles long before reaching this area, and the seafloor here lacks active volcanic or hydrothermal systems. The result is water with iron concentrations so low they are difficult to measure. Scientists studying the region have conducted experiments to test this. They added small amounts of iron to water samples collected from the area. In controlled conditions, the phytoplankton responded immediately. Their growth rates increased. Chlorophyll production rose. This confirmed that iron, not light or carbon dioxide, was the limiting factor. But in the natural environment, no iron arrives. So the phytoplankton remains stunted. Another factor contributing to the emptiness is the clarity of the water. In most parts of the ocean, suspended particles scatter and absorb light. This limits how deep sunlight can penetrate. At Point Nemo, the water is so clear that sunlight reaches unusually deep, sometimes more than 100 meters below the surface. You might think this would help phytoplankton. More light should mean more photosynthesis. But phytoplankton need nutrients, not just light. The deep penetration of light does not compensate for the lack of nitrogen, phosphorus, and iron. Instead, the clarity becomes a symptom of the problem. Clear water means few particles, few organisms, and low productivity. The deep sea beneath Point Nemo is equally barren. In productive ocean regions, organic material sinks from the surface to the seafloor. This marine snow feeds deep-sea ecosystems. But at Point Nemo, very little marine snow falls. The sparse surface life produces minimal waste. Deep-sea organisms must survive on a diet that is both scarce and unpredictable. Some species adapt by slowing their metabolism. They move less, reproduce less, and require less energy. Others scavenge, traveling long distances to find food. But overall, the deep-sea community here is one of the least dense on Earth. Scientists have used remotely operated vehicles to film the seafloor. The footage shows a sediment-covered plain with very few organisms. Occasionally, a sea cucumber or brittle star appears. But long stretches show nothing but mud. The sediment itself accumulates slowly. In productive regions, sediment is rich in organic material. Shells from plankton, fecal pellets from zooplankton, and fragments of larger organisms all contribute. At Point Nemo, sediment is mostly mineral particles that drifted from distant sources. Organic content is minimal. The lack of life has implications for global carbon cycling. Phytoplankton play a crucial role in removing carbon dioxide from the atmosphere. When they photosynthesize, they convert CO2 into organic matter. When they die, some of that carbon sinks to the deep ocean, where it remains for centuries. This process, called the biological pump, helps regulate Earth's climate. At Point Nemo, The biological pump operates at a fraction of its potential capacity. With so few phytoplankton, less carbon is removed from the atmosphere. The region contributes little to ocean-based carbon sequestration. As climate change progresses, this matters. Models predict that oligotrophic regions like the South Pacific Gyre may expand. Warmer temperatures strengthen stratification. This prevents nutrients from reaching the surface, further reducing productivity. If the gyre grows, the ocean's ability to absorb carbon may decline. This could accelerate atmospheric CO2 accumulation. Point Nemo, then, is not just a curiosity. It is a window into potential futures, a preview of what other ocean regions might become if warming continues. Scientists monitor this area closely for signs of change. They track chlorophyll levels, temperature profiles, and current patterns. So far, the region has remained stable. But stability here does not mean health. It means persistent scarcity, a system locked in a low-energy state. Understanding this science transforms how we see Point Nemo. It is not mysterious. It is the natural result of geography, chemistry, and physics, a place where the rules of oceanography produce emptiness. Not because the ocean is broken, but because the conditions necessary for abundance are absent. Science explains the emptiness, but it does not erase the human impulse to wonder, to imagine what might exist where so few have looked. Even when the evidence says otherwise, curiosity persists. Let us explore why. Humans are storytelling creatures. We look at blank spaces and fill them with possibilities. Uncharted forests might hide undiscovered species. Deep caves might contain ancient formations. Remote mountains might hold secrets. This impulse has driven exploration for millennia. It has led to genuine discoveries. New species, new ecosystems, new understanding. But it has also led to myths. Stories about places that exist more in imagination than reality. Point Nemo sits at the intersection of these impulses. It is real, measurable, and scientifically understood. But its remoteness and emptiness invite speculation. What if something lives in the deep that we have not found? What if the scarcity hides something rare? What if the isolation protects a secret? These questions are natural, and answering them requires balancing curiosity with evidence. Let us look at what might exist at Point Nemo and what almost certainly does not. In every remote place, people imagine hidden things. Creatures that avoid detection. Phenomena that defy explanation. But imagination and reality do not always align. At Point Nemo, reality is less dramatic than fiction, but no less interesting. The deep ocean has always been a source of mystery. For most of human history, we knew nothing about what lived below a few hundred meters. The pressure, the darkness, and the cold made exploration impossible. When technology finally allowed us to reach the deep, we found astonishing life. Fish with transparent bodies, octopuses that glow in the dark, worms that thrive near superheated vents. These discoveries fueled speculation. If such strange life exists in some deep-sea regions, what might exist in others? Point Nemo, being so remote and unexplored, became a natural target for this speculation. Perhaps there are species here that exist nowhere else. Perhaps the isolation has created unique evolutionary pressures. Perhaps something large and unknown hides in the depths. These ideas are appealing, but they do not align with what we know about deep-sea ecology. life in the ocean is constrained by energy availability. Organisms need food to survive. Food comes from sunlight, which drives photosynthesis, or from chemical energy, which emerges near hydrothermal vents. At Point Nemo, neither source is abundant. Sunlight reaches the surface, but without nutrients, phytoplankton cannot grow. The seafloor lacks active vents or significant geothermal activity. There is no energy input to support a diverse ecosystem. Any organisms living here must survive on the sparse supply of organic material that sinks from above. This limits the size and complexity of the ecosystem. Large predators require large prey populations. Large prey populations require abundant small organisms. Abundant small organisms require high primary productivity. Point Nemo has low primary productivity. Therefore, it cannot support large predators in significant numbers. The deep-sea organisms that do live here are likely small, slow-growing, and efficient. They resemble species found in other oligotrophic regions. Sea cucumbers that crawl across the sediment, feeding on organic particles. Brittle stars that scavenge whatever drifts within reach. Deep-sea fish with slow metabolisms and minimal energy requirements. These species are adapted to scarcity, not abundance. They do not thrive here. They merely persist. The idea of undiscovered species is not entirely unfounded. The deep sea remains one of the least explored environments on Earth. New species are described regularly, but most discoveries occur in regions with unique features. Hydrothermal vents, cold seeps, seamounts, trenches. These environments offer ecological niches that support specialized life. Point Nemo lacks these features. The seafloor here is relatively flat and featureless. There are no vents, no methane seeps, no unusual geological structures. It is a plain of sediment, stretched over thousands of square kilometers. Any undiscovered species here would likely be small invertebrates or microorganisms. They might be scientifically interesting, but they would not be dramatically different from known species. Another speculation involves large marine animals that pass through the region. Whales, for example, migrate across vast distances. Some species travel from polar feeding grounds to tropical breeding areas. Their routes might cross Point Nemo. If so, could the region serve as a resting point? A place where whales pause during long journeys? The evidence suggests otherwise. Whales do not rest in the middle of the ocean. They surface to breathe, but they do not stop moving for extended periods. And they prefer regions where food is available. Point Nemo offers no feeding opportunities. A whale crossing this area would move through quickly, conserving energy. It would not linger. Giant squid are another subject of speculation. These elusive creatures live in deep water and are rarely observed. Some people wonder if Point Nemo might host populations of giant squid or other large cephalopods. Again, the evidence is not supportive. Giant squid are predators. They feed on fish and smaller squid. Their presence depends on prey availability. At Point Nemo, prey is scarce. The low productivity means few fish inhabit the region. Without prey, predators cannot survive. If giant squid pass through Point Nemo, they do so briefly while traveling between more productive waters. Some speculation focuses on the spacecraft debris on the seafloor. Could these structures create artificial habitats? Could organisms colonize the metal surfaces, forming unique communities? This phenomenon, called biofouling, is well documented. When humans place structures in the ocean, organisms settle on them. Barnacles, algae, sponges, and corals can colonize artificial surfaces. Over time, these structures can support small ecosystems. But this requires two conditions. First, larvae or spores must reach the structure. Second, nutrients must be available to support growth. At Point Nemo, both conditions are barely met. The isolation means few larvae drift into the region, and the low nutrient levels limit growth, even if organisms do arrive. Any biofouling on the spacecraft debris would be minimal. A thin film of bacteria, perhaps. A few hardy invertebrates clinging to surfaces. But not the vibrant communities seen on shipwrecks in coastal waters. What about undiscovered geological features? Could the seafloor hide formations that have not been mapped? This is possible, but unlikely to be dramatic. Seafloor mapping has improved greatly in recent decades. Satellites measure subtle variations in the ocean surface caused by underwater topography. These measurements reveal seamounts, ridges, and trenches. Point Nemo has been surveyed, at least broadly. The seafloor is relatively flat. There may be small hills or depressions that have not been mapped in detail, but there are no signs of large, unusual structures. Another question involves the spacecraft debris itself. Could it pose environmental risks? Could it leak chemicals or radiation? Space agencies plan re-entries carefully to minimize such risks. Fuel is burned before re-entry. Batteries are discharged. Radioactive materials are avoided in most designs. The debris that reaches the seafloor is mostly inert metal. Steel, aluminium, titanium. These materials corrode slowly in cold, deep water. But they do not release harmful substances in significant quantities. The environmental impact is minimal, far less than the impact of industrial waste, agricultural runoff, or plastic pollution in coastal regions. So what does the quiet at Point Nemo hide? Very little. It hides sparse populations of known deep-sea organisms. It hides scattered fragments of spacecraft, slowly breaking down. It hides a seafloor covered in sediment, largely undisturbed. What it does not hide is mystery in the popular sense. No lost civilizations. No undiscovered megafauna. No anomalies that defy explanation. The quiet is simply the result of natural processes. Processes that create an environment where life struggles to gain a foothold. Understanding this does not diminish the region's significance. Point Nemo is remarkable precisely because it is so ordinary. It shows us what the ocean looks like when human influence is minimal, when nutrient availability is low, when isolation is complete. It is a baseline, a reference point, a reminder that not every place on Earth is rich with life. Some places are quiet, and in that quietness there is its own kind of meaning. We have explored the science, the history, and the speculation. Now, as our journey draws toward its end, one question remains. What does it mean to know a place like this exists? What does Point Nemo teach us about the planet and ourselves? Knowledge changes how we see the world. Before we knew about germs, disease seemed random. Before we mapped the oceans, their depths seemed infinite. Before we understood ecosystems, nature seemed chaotic. Each discovery adds structure to our understanding. It replaces mystery with explanation. But explanation does not erase wonder. It transforms it. Point Nemo is no longer a blank space on the map. It is a place we understand, a region defined by isolation, scarcity, and stability, a location where spacecraft rest and currents circle endlessly. Yet understanding it does not make it less significant. If anything, it becomes more meaningful, because it shows us something essential about Earth, about the ocean's vastness, about the limits of life, and about the consequences of human activity, even in the most remote places. As we reach the final chapter, let us consider what Point Nemo reveals. Not just about itself, but about the world we inhabit. In a world where every corner has been mapped and explored, empty places feel rare. Point Nemo reminds us that emptiness still exists, not as a failure or an absence, but as a natural condition, a part of the planet's diversity. Point Nemo challenges our assumptions about the ocean. We think of the sea as teeming with life. Fish, whales, coral, seabirds, dolphins. These images dominate our perception, but they represent only part of the story. Much of the ocean is more like Point Nemo than like a coral reef. Oligotrophic regions cover vast areas of the Pacific, Atlantic, and Indian Oceans. Together, they make up nearly 40% of the ocean's surface. These regions are often called ocean deserts. They are low in productivity, sparse in life, and isolated from nutrient sources. Point Nemo is simply the most extreme example. The most remote, the most isolated, the most empty. But it is not alone. Recognizing this helps us understand the ocean more accurately. The sea is not uniformly abundant. It is a mosaic of different environments, some rich, some poor, some dynamic, some stable. Each plays a role in the global system. Point Nemo's role is modest. It absorbs little carbon. It supports few organisms. It contributes minimally to global productivity. But its presence balances the system. The gyre that circles it redistributes heat. The stable conditions provide a reference point for scientists studying change. And the isolation makes it useful for safe spacecraft disposal. This last point is worth considering. The use of Point Nemo as a spacecraft cemetery raises questions about how we manage remote environments. Is it acceptable to use an empty place as a disposal site? Does the lack of life justify the practice? Or does every part of the ocean deserve protection, regardless of productivity? These are not easy questions, but the evidence suggests the practice is relatively benign. The debris is inert. It does not leak toxins or disturb ecosystems significantly. The amount of material is tiny compared to the scale of the ocean. And the alternative, allowing uncontrolled re-entries, poses greater risks. Still, the practice is a reminder that no place on Earth is truly untouched. Even the most remote ocean contains traces of human activity. Not just spacecraft debris, but microplastics, chemical pollutants, and atmospheric changes. Isolation does not equal immunity. The ocean connects all things. What happens in one region eventually affects others. Currents carry materials across vast distances. Atmospheric circulation spreads particles globally. Climate change alters temperature and chemistry everywhere. Point Nemo is protected by distance, but not forever. As the world changes, so will this region. Warming temperatures may strengthen stratification, reducing productivity further. or they may weaken the gyre, allowing more mixing. Ocean acidification may affect the few organisms that do live here. Changes in wind patterns may alter currents. Scientists cannot predict exactly how Point Nemo will change, but they know it will not remain static. Nothing in nature does. For now, though, the region remains much as it has been for millennia. A vast stretch of open water, clear, calm, and nearly lifeless, circled by currents that isolate it from the rest of the world. To stand at Point Nemo, if such a thing were possible, would be to experience the planet in its most elemental form. Water, air, light. No complexity, no distraction. Just the simple fact of existence. The horizon stretching unbroken. The sky arching overhead. The water rolling gently beneath you. It would be peaceful, perhaps, or unsettling, or both, but it would undeniably be real. A place where the usual markers of human life fall away, where proximity to others, access to resources, and connection to land all vanish. What remains is the ocean itself, indifferent, enduring, vast beyond comprehension. Point Nemo teaches us about limits, the limits of life, which cannot thrive without nutrients, the limits of exploration, which still leave vast areas unseen, the limits of isolation, which even in the digital age remains possible. It also teaches us about scale. The Earth is large enough to contain places where no one goes, where distance alone creates separation, where the forces of nature operate without interruption. These lessons are worth remembering. In a crowded world, we often forget that empty places exist. We assume every environment is accessible, every resource is available. But Point Nemo reminds us that the planet is not built for human convenience. It is built on physical principles. Currents, chemistry, distance, energy. These principles shape what is possible. And sometimes, what is possible is very little. The spacecraft resting on the seafloor add another layer to this meaning. They represent human ambition, our drive to explore beyond our planet, to build machines that orbit Earth and study the cosmos. But they also represent humility, because every machine eventually fails. Every mission eventually ends. And when it does, the machine returns to Earth. Not to a museum or a monument, but to the deep, where the ocean quietly reclaims it. There is something poetic about this cycle. Machines launched into the sky with fire and noise, returning to the sea in silence, sinking into darkness where they will never be seen again. It reminds us that even our greatest achievements are temporary. The ocean, meanwhile, continues. It was here long before humans existed. It will be here long after we are gone. Point Nemo will remain remote. The gyre will keep circling. The water will stay clear and empty. Not because of anything we do, but because that is what the ocean does in this part of the world. As we conclude this journey, it is worth reflecting on why we explored Point Nemo at all. Not because it is beautiful, though it has its own stark beauty. Not because it is dangerous, though isolation carries risks. But because it exists. And because understanding it helps us understand the world. Every place on Earth has a story. Even the empty ones. Especially the empty ones. Point Nemo's story is one of isolation, scarcity, and silence. A story shaped by currents, distance, and the limits of life. It is not a dramatic story. There are no heroes, no conflicts, no resolutions. Just the steady, patient rhythm of the ocean, rolling on day after day, unchanged, unchanging. And perhaps that is enough. Perhaps the lesson of Point Nemo is simply this. Not every place needs to be full. Not every space needs to be occupied. Some places exist to show us what the world looks like when we step back, when we let nature be what it is, without trying to fill it, fix it, or claim it. Point Nemo is one of those places. Remote, empty, and endlessly patient. A point on the map that represents the furthest edge of human presence. And in that distance, a kind of peace. The ocean continues its slow circulation. The spacecraft rest in darkness, and the water above them remains clear, calm, and impossibly far from everything. This is Point Nemo, the most isolated place on Earth. Not a mystery, not a monument, just a place, quiet, empty, and profoundly itself. Thank you for drifting with us across these remote waters. If this journey brought you calm, clarity, or simply a moment of peace, that is enough. Point Nemo will remain where it is, far from everything. And perhaps that is exactly where it should be. Until next time, rest well. Let your thoughts settle like sediment on the ocean floor. And remember that even in the emptiest places, there is meaning. You just have to listen for it